Hi, my name is Xavier Smith. I'm a writing junior at the University of Maryland, Baltimore County, where I'm studying computer engineering with a focus in electronic systems and communications. This summer, I've been working in the Research Laboratory of Electronics under the direction and supervision of Dr. Stephen Lieb, along with grad students Eric Ponce, Dan Menego, and Nicholas Hardy. My project's name was called Refocusing Analog Electronic Pedagogy to emphasize practical skill development within a PsoC environment. So what we're going to be talking about today is the motivation behind our project, the environment in which we conducted these experiments, the implementation of those experiments, along with future work and closing. So the motivation behind this project stems from emphasizing the importance of practical skills in electronics and electrical engineering curriculums, specifically speaking within the context of advanced high school and undergraduate students, ensuring that as they leave those curriculums, they get the theory that they need to be effective solving these technological solutions that involve electrical circuits. And so we wanted to do this through an analog electronic handbook that emphasizes that application of theory. And so we were thinking about three main things when we were developing these labs: accessibility, safety, and pedagogy. And so inside this environment that we were using is centered around this PsoC. PsoC stands for Programmable System on Chip. And the cool thing about this microcontroller is that it has programmable hardware through software or firmware. And so you can program it through ARM, which is assembly, C, or through this IDE called PsoC Creator, which has drag and drop components and that allows you to infinitely customize the circuit that we're creating. And so we wanted to interface this PsoC with an OLED. We have an OLED on board that's 64 by 128 pixels, along with a bank of LEDs and switches. And so we did that in the context of other circuits, but we're talking about these 4 circuits today. And so the first circuit that we're going to be talking about is the duty cycle to voltage converter. And what this circuit does is that it detects an average value of an input signal and displays that correlation to the brightness of an LED. And so we see here on the left, our PsoC schematic is we have a comparator, our low pass filter, and output buffer, and everything inside of here is internally within the PsoC, which is great. And so on the right we have our circuit diagram equivalent. So the cool thing about the circuit is that, specifically speaking about this comparator, we have an input triangle square wave of 7.813 kilohertz, with an input analog voltage between 0 and 5 volts that sets the pulse width modulated square wave, or the duty cycle of our square wave, which then gets put to a low pass filter. And a RC low pass filter only passes frequencies that are lower than its cutoff frequency, which we chose to be 106.103 hertz, and which only will allow that average value in that signal to be let through. And so we can see in our ability plot that any frequencies that are any frequencies that are lower than our cutoff frequency has a magnitude closer to 1. And the next circuit that we're going to be talking about is the amplitude detector, which is similar to the previous circuit, but it only detects the amplitude, not the average value, and it displays it through the relationship through the brightness of an LED. And so we see our PsoC schematic and our circuit diagram again. But the cool thing about the circuit and the difference between the circuit and the previous one is that this part of the circuit is the mathematical dual of the low pass filter. What this means is that is the opposite, which the high pass filter only allows higher frequencies to be let through, frequencies that are higher than its cutoff frequency, which is, we set it to be the same. But to get the amplitude out of a signal, whether it be sine, square, triangle, we need to rectify that signal. And so since we were using a sine wave inside of our filter, we needed to rectify that signal. And so because of safety reasons, we chose to do it digitally. Here we can see another Bode plot. All frequencies that are greater than its cutoff frequency has a magnitude that is greater than 1 or closer to 1. The next circuit we're going to be talking about is our band pass filter or audio selector. This is a cascade between the high pass and the low pass filter. What this does, it selects a signal and it plays it through a speaker. Here in the left you can see our PsoC schematic. But the cool thing about the circuit and the important part is the bandwidth and the quality factor, which these two things are representations of our circuit, where the bandwidth, the channel frequencies that are passed, and the quality factor is how selective that filter is. And so we put in the square wave frequencies between 0 and 5.3 kilohertz because our ears are low pass filters, so any frequencies that are greater than 18 kilohertz we are not able to hear. So here you can see our Bode plot, and you can see that our max amplitude is our center frequency, which is the geometric mean between the two half power frequencies. And so the last The last circuit that we're going to be talking about is our function generator, which externally a function generator is a device that generates different waveforms, but we wanted to do this within the scope of our environment and to ensure that the students can get the experience they need with that. And so here we can see on the left we have our PsoC schematic, and on the right our circuit diagram. But the important thing about this is that we have an integrated triangle wave, or a makeshift triangle wave that's integrated from our square wave. And so you can see it's a bit crude in terms of and relative to the square and the sine wave, which are integrated consists of an op amp that's in a capacitor. Capacitor is external, but the op amp is internal. And so here, the cool thing about this is we have an OLED display, or an oscilloscope. And this oscilloscope, this makeshift oscilloscope, uses an analog to digital converter that constructs our waveform through digital signals, through digital pixels, and it takes that analog voltage and it displays it on that OLED display, so the students can have an oscilloscope, which, just like the function generator externally, is extremely expensive. And so some of the feature work that I wanted to do with the main part of it is efficient data collection that allows the students to allows the teachers and the instructors to gain efficient information or assessments based upon whether or not the students are actually learning something, so we can better develop the labs. I would like to thank the UIs program at UMBC, the MSRP program at MIT, the Granger Energy Labs. I'd like to thank my mentor, Dr. Stephen Lieb, along with my grad students, Dan Monagle, Nicholas Howdy, Eric Potts, Nicole Skinner, and Joshua Talbot.